All right. Thank you all for joining us. My name is Amanda Reynolds, and I'm a program analyst with the Fire and Resource Assessment Program at CAL FIRE. I'm excited to welcome you to this presentation from one of our grantees, or two of our grantees in our Forest Health Research Program. We're joined today by Rebecca Wayman and Quinn Sorensen from UC Davis for the presentation, Dead Tree Removal After Drought-Induced Tree Mortality, Implications for Mixed Conifer Forest Recovery, Fuels, and Carbon. Before we get started, I have a little housekeeping to go over. This presentation is being recorded and it's going to be made available on our website along with information for future and past webinars and events. You are welcome to place any question. We welcome all of your questions, and we'll have a Q&A session at the end of the presentation. And you're welcome to place your question in the chat at any time during the presentation, or you can use the raise hand feature. I just realized that I didn't move forward on the slide for the housekeeping. And we'll get to your questions at the end of the presentation. Today's presentation is part of CAL FIRE's Forest Health Research Grant Program, funded in part by the California Climate Investments, which is putting cap-and-trade dollars to work in communities throughout California. This program aims to prioritize and fund research in forest health and fire science critical to the state of California, share scientific information, and support statewide plans, including the California Wildfire and Forest Resilience Action Plan. So without further ado, I will introduce our speakers. Rebecca Wayman is actually, let me stop sharing so that you can see everybody. Okay. So Rebecca Wayman is a research scientist at UC Davis. Her research focuses on effects and drivers of forest disturbances, such as wildfire and drought-induced tree mortality, and ecological impacts of forest management practices. Quinn Sorensen is a postdoc at UC Davis with roots in the Sierra Nevada. He schooled at UC Irvine for his bachelor's in science and UW-Madison for his PhD. He studied fire in several areas, and now he studies forests in the face of wildfire and tree mortality. And I will hand this over to you.
All right, is my screen or the first slide showing up?
I do not see it.
Okay. I clicked share. Let's see. Here we go. That should do it.
Perfect.
Yep, that it. Is that it?
Mm-hmm.
Okay. All right, well, thanks for joining us today. Quinn Sorensen and I will be presenting results from our study looking at the ecological outcomes of dead tree removal in areas of drought and bark beetle-induced tree mortality in the Sierra Nevada. I will start by introducing the project and providing some context, and then I'll turn it over to Quinn, and he will present results on tree regeneration. Following that, I will present results on the understory plant community, and finally we'll return to Quinn and he'll talk about fuels, modeled future fire severity, and carbon. And so first I'd like to just draw your attention to this photo, and you can take a look at it to see, get a sense of what the mortality sometimes looked like in the areas of the central and southern Sierra Nevada that we studied. So I'll start with some background on the tree mortality event. These maps from the Forest Service show cumulative tree mortality progression from 2015 to 2018. And between 2010 and 2017, an estimated 129 million trees died in California due to drought-related causes. Note that the most severe mortality is concentrated in the central and the southern Sierra, and that the peak mortality was around 2015 and 2016, although it continued and actually still continues. A main driver of this native bark beetle epidemic, to simplify, was trees being water stressed. And water stress in this case is not just due to hot and dry conditions, but also to unhealthy, overcrowded forests with high water competition between trees. And since the forced cessation of indigenous burning practices and the initiation of active fire suppression, these forests have become exceedingly dense, so water stress during this extreme drought was exacerbated. Native bark beetles were able to overwhelm tree defenses, and the result was massive amounts of conifer mortality in the Sierras, and this has been unprecedented in the scientific record. So one outcome of this massive tree mortality event is the conversion of live fuels to dead ones and the rearrangement of fuels over time from the forest canopy to the forest floor. Resource managers became concerned about the potentially increased risk of severe fire. And one way to mitigate this risk is to cut and remove standing dead fuels. And our study aim was to examine the effects of this dead tree removal on key ecological outcomes and how they compare with outcomes in untreated areas. Specifically, we looked at outcomes that are both targets of fuel reduction treatments, in our case, fuels, and modeled future fire severity, and non-target or secondary outcomes, including tree regeneration, understory plant community, and carbon. And we wanted to look at how management affects forest recovery from this tree mortality event from all of these angles. So to do this, we identified areas of high tree mortality where dead trees were cut and removed from the site. We only included sites where the prescription was to remove the dead trees as opposed to cutting and leaving. We established paired treated and untreated plots on either side of the treatment boundary, and we ensured that the treatment boundary was ecologically arbitrary. Our control plots had similar slope, aspect, topography, tree species composition, and pre-treatment tree mortality levels as their paired treated plot. And in these photos on the left, we have examples of plots that we'll refer to as controls or no removal or untreated. And on the right are treated plots where dead trees were removed. Just to give you a sense of what the treatments look like and what the controls look like. We established a total of 122 plots or 61 plot pairs in 6 sites spanning a wide latitudinal gradient across the central and southern Sierra and across several different ownerships, although the majority were on national forest. We sampled within circular plots that were 1/10 acre or 0.04 hectares, and we collected data on tree regeneration, understory species, forest structure and composition, ground covers such as rock litter, bare soil, downed woody debris with Brown's fuels transects, and standard site physical characteristics. Sampling occurred in 2020 and 2021. And remember, the bulk of the tree mortality in this area occurred in 2015 and 2016, also into 2017. And dead tree removal in this case occurred largely between 2017 and 2020. And so when looking at the effects of drought mortality, it's really important to pay attention to the time since disturbance as the structure and spatial arrangement of the dead material changes over time. And so for our study, we sampled roughly 4 to 6 years after the bulk of tree mortality occurred. And it's just important to keep in mind that all of our results reflect initial outcomes in the early years post-mortality and post-treatment. So before I describe what the treatments at our study sites looked like, I'll take a brief interlude into a question we get a lot, which is, how does this drought and bark beetle disturbance differ from frequent low severity fire to which Sierra mixed conifer forests are adapted? And so I've just outlined kind of some basic differences here in what you might expect between these two disturbances regarding surface fuels, soil chemistry, and really importantly, the demographics of the trees that were killed by the disturbance. So unlike frequent fire, the bark beetle outbreak primarily affected mid to large diameter trees. And in the bark beetle drought disturbance, large numbers of fire-adapted pines were killed. other species as well, but typically the fire-adapted pines are faring better, have lower mortality in the frequent fire disturbance. So now I'll give a brief overview of what the treatments or the dead tree removal looked like and what the effects on the understory or the forest environment were. We used mixed effects models to examine differences between our paired plots with dead tree removal and no removal. And for ground covers, bare ground cover was higher in treatments. Litter depth was lower in treatments. And fine fuel mass, which includes 1 hour, 110 and 100 hour fuels, or fuels less than, woody fuels less than 7.6 centimeters diameter, did not differ. Total coarse woody debris, which are 1,000-hour fuels or fuels greater than 7.6 centimeters diameter, did not differ between treatments and controls. But when we break coarse woody debris out into sound and rotten, so sound being the more recent or younger fuels in decay classes 1 and 2, and rotten being older fuels in decay classes 3, 4, and 5, we see that in our treatments, sound fuels were had greater mass. There was greater sound fuel mass in the treatments, and there was lower rotten fuel mass in the treatments. And finally, regarding trees, although the treatments were prescribed to target dead trees, small live tree density was lower in the treatments. And with small trees, we defined here as 7.6 to 30 centimeters diameter breast height. And live tree cover was lower in treatments, primarily driven by changes to those small trees. And as we would expect and hope, dead tree density was lower in our treatments. So I will now turn it over to Quinn, who is going to discuss regeneration. And I will stop sharing and Quinn will begin his share. I will stop sharing, I promise you. All right.
I think we may have lost Quinn.
I see him on here, or I see his name on here.
Oh, you do? Oh, here he is. Okay. Okay. You are in as a participant, though. Again, let me find you and make you a presenter. Actually, oh, there you are. Sorry about that. Make a presenter. Yep. All right. You are muted. Oh, there
Okay.
you go.
Yeah. All right. Hi, everyone. I'm Quinn Sorensen, and I will start sharing in just a sec. Okay, so first we wanted to talk about how dead tree removal affects the regeneration of the forest. And so you can imagine that when heavy equipment comes through, that it creates a lot of different conditions in the environment. So Becky went through that. And the ones that we think or we thought could potentially affect tree regeneration were things like the soil disturbance, creating microsites for establishment, maybe elevating the access to sunlight and providing more opportunities for growth. And so we thought that we needed to examine how much regeneration is occurring and ensure that this salvage or this dead tree removal wasn't negatively impacting future forests. And so for this data set, we collected seedling density and sapling density. And we wanted to know whether or not the seedling and sapling regeneration was reduced and by how much. We wanted to know if it affected species differently. These differences in the environmental conditions that dead tree removal create might favor certain species, perhaps the more sun tolerant species. And then we wanted to know if they responded differently by age, so whether seedlings or saplings behave differently. And so here's the result from the model. On the bottom, we have dead tree removal and no removal throughout the presentation. The green will always be the dead tree removal, and the brown will always be the no removal, the control. And so what we can see is that there is a significant decrease in seedling density, about a 60% decline in total species. But species responded differently. So here are the 4 major species that we measured in our sampling. And 3 of them responded to the dead tree removal, while 2 of them didn't. So white fir had the most significant decline. It was the most common seedling, and it's likely what's driving most of the total decline in seedling density. Incense cedar and black oaks, there's no change in or no difference in species or in density, while sugar pine declined. But interestingly, yellow pines actually increased in their seedling density. And so while it looks like either all the rest are having no effect or a decline, the yellow pines are responding favorably to these new environments. And a very similar pattern occurred when we look at saplings. And so here we see about a 70% or 65% decline in density. And for saplings, we only had enough records to analyze it for the white fir and the incense cedar. And unlike the seedlings, the incense cedar here actually declined, and white fir was similar to the species seedling density. And so the takeaways we have from this is that dead tree removal may decrease the number of regenerating trees, but it's not completely wiping them out. It's a substantial decline, but it's not. I don't know. It's up to your interpretation whether or not those densities are good or bad or close to the target that you would want for regeneration. Another thing we found was that the species composition in the future might be influenced. If and like yellow pines may be benefiting far more than the other tree species into the future. And we can imagine that the dead tree removal is having effects on the environment that are favorable to establishment, and they reduce competitor seedlings and saplings. And so it might, over time, provide a shift in composition to an increase in yellow pines and a decrease in firs. That it may take time for those patterns to develop, but tree regeneration can have long-lasting impacts on a forest over hundreds of years. And so this may be a tool to help guide the forest towards the targets that we want. Okay, and I'm going to switch back to Becky.
Oh,
Becky, you're muted.
Becky, you're muted. Or let me see if I can.
Okay, there we go. Sorry about that. All right, and you can see my screen?
Yes.
Okay. So I will pivot over to the understory plant community and our results that we found there. So the understory community, as we've been talking about, has been subjected to multiple interacting stressors. First, this long-term departure from the historic fire regime, then the recent extreme drought and severe tree mortality. And these compounding stressors were novel in severity and extent. And cumulative effects on the understory plant community, to our knowledge, have not been documented. And crucially, the impacts to the understory plant community from management responses to these ecosystem stressors are also unknown. And that is the focus of this analysis. And remember that changes to the understory environment caused by this drought-induced disturbance are not equivalent to the impacts of frequent low-severity fire in all cases, although both disturbances do likely increase understory light levels. So a central question is whether post-drought management actions designed to mitigate severe wildfire risk from tree mortality create conditions that mimic historical ecosystem features to which the understory plant community is adapted, thereby potentially maximizing plant species richness or at least increasing it, or whether such management shifts ecosystem features away from those conditions. So we wanted to examine the post-mortality and management effects on plant species diversity, cover, and composition. So we had three study questions for this part of the study that we asked with regards to management impacts on the understory plant community. And those are, first, does dead tree removal affect understory plant species diversity? And if so, what are the associated environmental factors? Second, how does dead tree removal affect understory vegetation cover? And third, does dead tree removal alter understory plant community composition? And if so, which environmental characteristics and plant functional groups are associated with the changes? So back to question one, does dead tree removal affect diversity, and what are the associated environmental factors? So to compare alpha richness, or the number of species at the plot level between treated and untreated plots, we again ran generalized linear mixed effects models with site as a random effect, and pair ID was nested within site. And I'm going to show results for richness here, but Shannon's diversity, which incorporates both richness and evenness, follows the same patterns, and we found no differences in evenness, so I'm just focusing on richness. And again, green is the treated or the plots with dead tree removal, and brown are the untreated controls. And note the different y-axis scale across the different subgroups. They're not on the same scale. So total understory species richness was 22% higher in treated plots, and it was higher across all subgroups analyzed in the treatments. Annual herbs made up a small portion of species in the treated and untreated plots, but annual richness was 70% higher in treated than untreated plots. Perennial richness was predicted to be 27% higher, and shrub richness 19% higher. Also of note, we had very few non-native species and very few occurrences of those species, but plots with dead tree removal were predicted to contain 194% more non-native species than plots with no removal. So much higher likelihood of finding a non-native in the treatment. We examined environmental conditions associated with total understory species richness and richness by growth form. And this figure shows marginal effects plots for all predictors selected to remain in the best models for total, annual, perennial, and shrub richness. And marginal effects were calculated for treated plots and by holding all other variables constant at their median value. Shading is the standard error, and note that the scale for the subgroups is on the right, and that scale is it's half the scale of the scale for total richness. Was just that scale is on the left, and total richness is shown in the dark gray, annual richness in yellow, perennial in green, and shrub richness is in light gray. And the environmental conditions associated with understory richness did differ by growth form. Elevation and topographic relative moisture index, which is what the TRMI stands for, are not affected by treatment. So I am going to draw your attention to the lower left, which is live tree cover. And this was negatively associated with total and annual species richness. Here we take a look at our species accumulation curve, which summarizes gamma richness. So alpha richness being richness at the plot level, and gamma richness is the richness across all plots. And these curves represent the mean number of species accumulated with increasing sampling intensity, averaged across 10,000 iterations of randomly selected plot pairs. And like alpha richness, gamma richness was higher in treated plots. So as we increase our sampling effort to more and more plots, we keep adding species at a faster rate in treated plots than in controls. So our second question is, how does dead tree removal affect understory vegetation cover? And total understory vegetation cover was 30% lower in treated plots than in untreated plots, but this varied among subgroups. So non-natives and annuals had 2 and 3 times higher cover with treatment, while saplings, which aren't shown here, they had 3 times lower cover with treatment. And changes in shrub cover was lower with treatment, although it was a pretty modest difference. But changes in shrub cover likely drive the difference in overall cover, since shrubs make up the bulk of species cover. And our third question, does dead tree removal alter understory plant community composition? And if so, which environmental characteristics and plant functional groups are associated with the changes? So this figure I find very beautiful, and Quinn made this figure. It shows species rank abundance for the most common 68 species in each treatment type. And if you can't see or interpret the species codes, don't worry, that's not really the point of me showing this to you. Just know that each of those 6-letter codes represents a species. And there's a lot going on here, so I'm going to take a moment to orient you. Along the x-axis, we have, along the y-axis, we have that list of species. And along the x-axis is the number of plots where that species was documented. So those green bars or the brown bars represent the number of plots, either for treatments or controls where that species was documented. And so for example, at the top, we have Ribes roselii, and that was the most common species in both treated and untreated plots. And it occurred in about 60 plots in the treatments and about 50 plots in the untreated, for the untreated plots. Now the lines in the middle are connecting the same species, and their color corresponds to whether the species had more occurrences in treatments or controls. So a green line means it had more occurrences in the treatment, and a brown line means more in the controls, and yellow means it had the same number of occurrences in each. So now the first thing I want you to notice is that, especially for the higher ranking species, if you look at that, the group of species at the top, you'll see that the most common species are pretty much the same in treatments and controls. And then if you look further down to the less, kind of the moderately and the less common species, and again, this only shows the top 68 species out of 170, I believe, or about that. So it's that next groups of species, the moderately common ones, that show more dramatic changes in their occurrence between treatments and controls. So this is suggesting what might be fairly intuitive, that some of the most common species may be common because they're pretty flexible in their habitat requirements, but any differences in community composition are happening at the more moderately common and less common species. And just of note, across all species documented, 119 were found in both the dead tree removal and no removal plots. 44 were unique to treatments, and 14 were unique to untreated.
10 minutes.
Okay. So this is a non-metric multi-dimensional scaling ordination on presence-absence data for species with more than 3 occurrences in the data set. It shows plots in species space, and it can be interpreted that plots closer to each other have more similar species composition. And overlaid onto this are environmental variables that had a significant correlation with species composition, and vectors represent the direction and the magnitude of change of those variables. And the ellipses are 1 standard deviation away from the centroid of all the plots in the sample. So if you recall that the environmental variables most highly associated with species richness in our models were tree cover, topographic relative moisture index, and elevation. And the take home here really is that across all the plots on this wide latitudinal gradient, there's not a highly obvious difference in community composition between treatments and controls, since you don't see really obvious clustering of the same colors of points, but you do see a slight difference. And when we ran a Permanova to test for compositional differences, it is significant in the sample. And the plant community and treatments is just shifted slightly towards higher bare ground, lower tree cover, and lower fine fuels and litter. I'm going to just be real quick. We ran on the indicator species analysis. We did run an indicator species analysis, and I think the take home here is that we had more indicators were annuals and short-lived perennials for the treatments, and in the controls we had no annual indicators and 2 shrubs as significant indicators. And this is my summary slide for this. with the removal of recently dead trees in the early post-years treatment, this was associated with increased understory plant species diversity at both the alpha and gamma scales. And this was driven by richness and driven by increases in annual plants. And these findings align fairly well with studies looking at the effects of forest thinning in undisturbed montane conifer forests of the Western US. Those studies tend to document either no change in understory plant diversity with thinning treatments or an initial increase in diversity or richness after thinning. And so it is possible that post-mortality dead tree removal promotes richness at the plot or larger scales via intermediate disturbance intensity, as it did seem to create suitable microsite conditions for post-disturbance colonizers. But while largely maintaining habitat for existing and later successional species. So the treatment may emulate the range of disturbance intensities to which species in this understory plant community evolved, or at least push things a little bit in that direction. However, it is unknown whether a higher intensity of treatment disturbance would further increase initial species diversity over what we observed or not. So I will now turn it back over to Quinn. As I get to the stop share button here. And he will wrap up our final analyses for you. Are you ready, Quinn?
Yeah, sorry. Okay, oops. So in
5
addition
minutes.
to species diversity, we wanted to look at how these treatments will affect the forest over the long term. And so I'll remind you, Becky talked about at the beginning how removing dead trees causes changes in fuels. When the trees are cut, a lot of the branches become slash, and we noticed observationally a pretty large pulse of smaller fuels. And while the difference wasn't significant, there may have been a hidden trend in at least the smaller surface fuels. And so we wanted to understand what pulling out the bole of a tree and leaving slash in a removal site, how that affects fire, or how it affects fuels over time. So we wanted to know in which places fuels are accumulating, how the differences between the treatments, whether they converge or diverge over time. And we wanted to understand fire behavior. So studying the fuels and changes in the fuels can lead to differences in how the forest responds to fire. And so what I mean by that is, rather than having coarse woody debris slowly fall over decades, and having large coarse woody debris remain in the trunk of the tree, we're changing the structure of the fuels. And while one of the aims of dead tree removal can be reducing fire risk, we don't know how that would play out. So we wanted to know how it would affect fire behavior and the torching potential and the severity of the fire, how many trees die. And then we also wanted to understand how the changes in forest structure now can be simulated out a century to understand if you remove the carbon from the forest in the form of the timber, will it come back? Will it reach equilibrium with the controls, or will it still have a lower carbon? And so to do this, we use the forest vegetation simulator. And we use that to measure, or we use the measures in our plots, and we fed it into the simulator, which simulates the development of a forest given the starting conditions. And so we put in things like number of trees, basal area. We put in all of our fuels information, what species, and the simulator uses established rates of transition from seed to seedling to sapling to overstory tree, and death rates and fuel drop rates, to iteratively look forward in time to see what will change in the fuels, fire, and carbon. And as I go through the results, I'll tell you in more detail about the response variables we chose to examine these changes over time. And there's a caveat that the forest vegetation simulator isn't perfect. And so there might be some funky patterns based on the assumptions, like that no fire has come through yet, and that the only recruitment into the canopy comes from the seedlings and saplings that are already on the ground. Okay, so starting with standing dead fuel. So this is the total standing dead fuel in the forest. And I chose this one first because it's the most intuitive. So if you go in and cut down dead trees, you're going to have a lot less standing dead wood or fuels. And so what's interesting is how the fuels accumulate, the standing fuels accumulate over time in parallel with each other. And so likely because of the spore simulator assumes a constant rate of death and inputs of the fuels, it's showing that if no fire were to come through, the areas that did not have dead tree removal would also continue to accumulate fuels. And then I want to point out in 2025, you see a significant jump in the control. And so likely this is because the standing dead trees that were in those areas likely were from the mass mortality event. And so that's why we see a large pulse after 2020. And then the model assumes normal climate with some extremes, but on average, an intermediate climate. And I wanted to point out that even in 100 years, the predictions are that there's still going to be 50% less standing dead tree or dead fuels. Okay, so live fuels is a little different. It may look like the controls are somehow having or that they somehow have fewer trees in them, but these differences are not statistically significant. Although in the year 2070 and 2080, they were barely significantly different. And given the sort of imprecise nature of using these simulations, my takeaway is that in essence, there's not really an effect of dead tree removal on the standing live fuel. All right, but if we look at surface fuels, an interesting story occurs. So, unlike the standing dead, there's not a large pulse in the controls. There's an increase in the rate of fuel dropping to the surface. And you can see that in the first 30 to 40 years. But you'll notice that in 2020, it starts out with no difference. And so if we can keep these forests, or if we can increase the time between fire in these forests, then the effects of our treatment, even if they're slow to start, given time, they can reduce the fuel loads on the surface. Okay, so what happens if fire does come through, though? So in the following simulations, we calculated the probability of torching and the percent basal area tree mortality. So the first variable, probability of torching, it just means the probability that a fire on the surface would be able to reach the canopy of a tree in a small a quarter acre area. So at least one of the trees will torch. And that gives you an idea of the likelihood of a surface fire potentially turning into a crown fire. And then the percent basal area mortality is simply just the relative amount of basal area in the forest that represents going from live trees to dead trees when a fire comes through. And you can think of it as fire severity.
Just a
Okay,
reminder,
so
you have about 9 minutes till the top of the hour.
okay. And so this is one of our somewhat surprising but interesting findings. We see that the probability of torching, or the torch probability, is actually greater in the year we sampled. And as time goes on, the simulator assumes the fuels will decay, and after about 10 or 5 to 10 years, there's a switch where the torch potential of the control is a lot higher, and it's sustained and being high for nearly a century. And I want to point out how if you look at the year 2030, you can see that the control takes another 30 years to get to the point that or the torch potential that the treated plots had. And so by removing dead trees, we can hasten this process of fuels falling and leaving the system, or leaving the system in the form of decay, which can translate to changes in fire severity. And so there's more to fire than just probability of torching, which I'm sure everybody in this audience knows. And while we've looked at some variables that also contribute to the mortality, we didn't have time to go over all of them. But what I want to point out here is similar to the torching potential. There's a hastening of changes in the severity of fire or basal area mortality. So similar to torching, the first year there's high probability of basal area mortality. And I'll just start saying mortality from now on. And that the mortality for trees after fire decreases much more rapidly. And if you look at 2030 again, up to the green dot, and follow it over to 2070, the brown dot, by removing dead trees, we're hastening the stability or lessening the fire risk rather, by about 30 years. And this has implications for management and motivating managers to see dead tree removal as a possible way to reduce the fire risk on their landscape. And I also want to point out that even after 100 years, even though this is a simulation and the actual numbers would be different, the basal area mortality on average is around 10 to 15%, while in the areas where the dead trees were not removed, that's about 25%. And then finally, I want to go over how this all ends up affecting carbon. And so, maybe not surprisingly, total forest carbon is reduced when you remove dead trees. And so we were curious to see if the carbon stocks in the forest would catch up, or if the rate of accumulation of carbon would be greater in the younger forests, or the treated forest. However, maybe we were too hopeful because it appears that the ability of the forest to sequester carbon, it increases, or the storing of the carbon increases, however, in parallel with and without dead tree removal. And so by removing dead trees, we're reducing the actual carbon that's in the forest. But I want to make a caveat that while the carbon in the trees is not accounted for in the forest after it's removed, if it's used to produce timber, then that timber the carbon in that timber won't be entering the atmosphere quickly. And of course, there's carbon emissions from the production of the timber, but we could assume that at least a portion of it would be pulled out of the forest and stored longer term. Okay, so what do we learn? So the pulse of surface fuels from dead tree removal, it created an environment that in the short term increased or maintained the risk of a severe fire, and the ability of the flame to reach the canopy actually increased. But it may be effective at reducing severe fire over a longer period. And so if these efforts were implemented, then the forest would only have to remain without fire for 10 years in order for the benefits of removing fuels to be seen. And while carbon stocks may have been lowered, and the simulator estimated that it would take longer than 100 years to reach an equilibrium, at least some of that carbon is being used. Hopefully, if it's a harvest for timber, a salvage harvest, then hopefully there's a economic incentive as well. Okay, and I'm going to turn it back to Rebecca. Close this out.
Becky, do you want to address any of these questions that you've done a great job of answering over on the chat?
Sorry, Dave, what was that?
I was going to say, do you want to address any of the questions in the chat that you've actually texted in some responses for?
I could. I know that, and maybe Quinn can take a look at the chat too, because there were some questions on the units on the figures. Yeah, and real quick, just I want to thank. Here's our thank you slide. Hopefully did that come up? Yeah.
Yes.
Because we had fabulous field crews and a lot of people have helped on this project, and thanks to the CAL FIRE for the funding for the project. Yeah, do you mean to expand on any of the questions that were back in the chat here?
Well, I haven't been on one of these in a while, so Amanda might comment. We are at a minute past 4. Amanda, have we typically run over and allowed people to just sort of work through the Q&A if it does kind of roll over?
Yeah. Yeah, it's yes. I will end the recording before we go into the Q&A. But I also wanted to thank you both again very much for presenting today. It was a really interesting presentation. It's really nice to see everything kind of come to life. So
thank you for having
quite
us,
wonderful.
and thanks to everyone for showing up and listening.
Awesome. I'm going to stop the recording and we can move on to the Q&A for anyone who wants to keep going.
So the first question came in from Joe.